So let's start the recording. And I am going to share with you just a blank whiteboard for now. And I specifically want to discuss question 2. Question 2 in the assignment that asks about UA. It says in Vogler, it gives a UA value of, I think, 10. Now, I'm not sure about the units, so I'm not going to quote it here, but look at that units that Vogler gives it in, and I ask you whether you think this is a realistic value, and it's for 20 marks. So obviously that cannot be yes it is or no it is not. I want some analysis on this. And the reason being, I want you to be reminded of where does these values come from? How will I have to calculate them when I have to do a design? Okay. So first off, this A has to do with the diameters of the tubes in your reactor. It's directly proportional or inversely proportional, sorry, to the diameters of the tubes in your reactor. If you have a non-adiabatic reactor, you will never, ever have just one big single tube, because the heat transfer, you will definitely have hot spots, especially if so no single tubes, because the rate of heat transfer will not be the same, or well, depending on, it will be the same, but you're going to have hot spots here in the middle, and you just have the heat transfer area here at the ends of, so no single tube. So what that reactor of Vogler hides from you is that it is in fact a packed bed reactor. That is a catalyzed reaction. He gives you the bed density. So you can calculate, and then he gives you just one big volume for his catalyst, or for his reactor. That big volume must consist out of lots of tubes. And he doesn't tell you, so you've got no information to base this on, is how many tubes do you have, Vogler? And what is the diameter of each of your tubes, Vogler? So what do I expect you to do is I expect you to see for typical diameters, does it fall in a typical range? If I, for instance, have a volume of 10 cubic meters, right, and I choose a number of tubes of 80, okay, what must the tube diameter then be, okay, in order to fit in there? But now what else do I need? So the tube diameter, ching, ching, the tube diameter will give me the cross-sectional area, okay? But I still, now if I've got that, I will subsequently be able to calculate so tube diameter and length, those are both unknowns in that relationship. So the volume of each tube can be calculated by its cross-sectional area times its length. This you have control over, the design engineer, because you choose the tube diameter. You choose the tube diameter. The length you have control over, because you actually choose the number of tubes. Okay, so it's a interplay between I must fit this amount of catalyst in this amount of tubes, and I can change the amount of tubes, I can change the diameter of the tubes, I can change the length of the tubes, and one of them must be a loose variable, if you understand what I'm saying. If I can't fix all three of them simultaneously, because I can't fix the diameter and the length and the number of tubes. So I'm going to leave you at that. Play around with this. Remember, look at realistic tube diameters. And what is a realistic tube diameter? So some design aspects here that we are going to discuss. You will base that on typical sizes of tubes that you can find. Sizes of tubes that you can find. 20 millimeters, that's industrially available for the material of construction that you are going to be using. Another thing that is important is if I now zoom in on one tube, this is one tube, and it's packed with catalyst beads. Packed with catalyst beads. There we go. Packed with catalyst beads. I want the ratio of the diameter of my tube over the diameter of my catalyst beads to be relatively large, preferably in the area of 15 or even 20. Otherwise, it's going to look like this. I'm going to have that, and I'm going to have big catalysts, and the wall, the fact that stuff is being constrained by the wall, is going to result in huge porosity differences in my bed. So I'm going to have a larger than expected bed porosity because the wall interferes with my packing. If this is true, if it's a relatively large tube to particle diameter, it implies that the porosity, regardless of whether I change the particle size, is pretty much going to be equal to that 40% value, bed porosity, that I quote in many of your packed bed reactor ducts. Can I have some questions on this? I've spoken a lot now. Anybody with some questions? Nothing? Okay, so what that question implies that I want you just to think about that A. Right, and how do I get A from Vogler's stuff? So a hint that I want to give you is let's start with U. Let's start with U. Yes, 100 tubes is definitely a reasonable number. Okay, 100 tubes is a reasonable number. Let me give you something else that's reasonable. If I look at my tube bundle diameter, and that normally I leave all this for the students to figure out for themselves in the design part. Yes, of course you do. So, and that is in the design part. That is important that I see that you learn this. But now I thought, let me just throw in some information that may be useful because it's all heuristics. Typically, the length over the diameter, that ratio of a reactor is, the figures quoted between 2 and 5 is realistic. 3 is popular, right? This ratio, okay? And this length over diameter, that refers to this whole bundle diameter of your tubes. So it's not just the tube, one tube diameter. And then I think you've done this in CIO or C, yeah, where when you have tubes, you have a certain pitch, right? So that's typically that you've learned in heat transfer design. I've got a certain pitch in order to discover if I've got 100 tubes, and I must arrange them in a certain pitch arrangement, square pitch or triangular pitch, or I can have square pitch. And now I arrange 100 tubes. This is what my bundle diameter will be. So this is the whole bundle, the whole diameter of your reactor. So this is something I look at when I evaluate your designs. Do they look pretty? Do they fall in this range? And you have control over this because the number of tubes that you specify and their diameter and the amount of catalyst that you must fit in there in order to bring about a certain conversion, you must decide. So, yes, I don't know, does this help? I hope. Right, I give some, you must save this lecture. I give some summary hints at the start of your reactor design process next semester. I always ask Mike just to give you some summary hints on, what to look for, typical L over D values as a reminder. But this is why it's important to keep these heuristics in mind, especially if you're a first-time designer. And remember, you are never just going to have 2 weeks. Next semester, you're going to have 2 weeks to design a reactor. You will not have 2 weeks if you design an actual reactor, and you will work in a whole team of people, a whole team of people that's experts in the field, that has got some experience, hopefully, that can work with you if you end up in a design company where you have to design reactors. And what they also use is they use these kinds of heuristics to say, okay, we don't want the pressure drop to be too high. What affects the pressure drop? And now you should be aware of that pressure drop. We don't want the flow rate through our reactor to be too low. If I've got a very low flow rate, I've got such a low linear velocity that I'm going to have mass transfer effects. And that is what we will get to after the recess, mass transfer effects. If I have a too fat reactor, so if my reactor is very fat, and I've got little short tubes in there, I must come from a single pipe, and I must now ensure that they are distributed evenly over all my tubes. And that is why we have suggestions for don't make your L over D value too small. So for this L over D value, this is going to be much less than 1. So it's going to be very difficult to distribute the flow over the number of tubes. Okay, right. So what I also want to show you is in further on this UA. Typical U. There we go. Done. Right. So let me just zoom. I'm zooming out again. So what this is, I just Googled this quickly this morning, right? And you should find this in your Perry's or in your CIO notes from when you did heat transfer, is that we can find typical overall heat transfer values just to give us an idea. And you can use that when you start with that question 2 in your assignment. To see, okay, first you need to figure out what is my cold fluid and what is my hot fluid. Your cold fluid in this case will be your gases that must react. So it's not on this list. There are 75 more rows. I think this is from Engineering Toolbox. But find a reputable source like your textbooks. And what is your hot fluid going to be? And that hot fluid that Vogler wants you to use must have a temperature of 1000 Kelvin, the utility. So you will have to do some independent research to see, can I find a utility with this high temperature? And if I have that, what is a typical range of U values? And if I now use a typical range of U values, and Vogler says that his UA is whatever, okay, and I choose that, his A, in other words, is whatever his A is, and is that realistic? What does it imply for how his reactor will look? Okay, so this is what I want you to keep in mind when you do that part, because in the end in CPJ, if you should design a packed bed reactor, you will have to not just find, I see people in desperation, they just use my TUT values that I give for UA. In that one TUT that we did on changing the number of tubes, UA is equal to whatever Elizabeth gave us. That's not the truth. No? The truth is that you actually have to calculate that U, and you have to specify your reactor, and that will affect A. The diameter of your tubes that you specify, the number of tubes must all chow up the amount of catalyst that is needed. So what is fixed in your assignment is the amount of catalyst that you are needed linked to the 10 cubic meter reactor that must be designed and the bed density that is specified. Right. So I don't see any questions popping up, so I'm going to go to the next slide. And this is also just copied from summerengineeringtoolbox.com, but I just wanted a quick reminder because I knew you were supposed to do this in your design subject CIO, is what affects this U? How will we were? Oh, Nia, you were definitely calculating seriously. Ding, ding, ding. Let me just write that 1 over the overall, the sum of resistances. Thank you. We did. Okay, look, don't worry. People forget stuff, and you will pick it up very quickly. You've got the internal heat transfer coefficient. You've got the thickness of your layers, sum of the thicknesses of your layers divided there. What is that thing called? Conduction. My word, thermal conductivity of the different layers. So if you have a tube and you've got insulation, but you will be stupid to put insulation on your tube, and then you've got the outside heat transfer coefficient. So whatever is flowing inside the tube and what is outside the tube, and these parameters, does the terms Prandtl, Sherwood ring any bells? They are functions of how fast stuff flows in your tube. So ultimately, they are also going to be a function of your tube diameter. But you will be forgiven if you don't incorporate that in your current design. If you just check, is it a realistic value at least for you? And when you do your ultimate design and you have to incorporate a heat exchanger, I suggest you start with typical U values. until you have fine-tuned your design to a point where you say, okay, this is now the area that I have chosen, and based on this area, I can now calculate internal and out H in and H out heat transfer coefficients using my Prandtl number. Study. Really? Sure. Okay, I will follow up. Did you do heat exchanger designs?
Yes, ma'am, we did it. It's more of an inside joke.
Oh, is it an inside joke? Okay, thank you very much. Otherwise, I was on the warpath. I was going to have a talk to some of my colleagues. Okay, right. But this is what I want you to, maybe not necessarily for the assignment, so depending on, once again, on your capacity, on how much detail you want to think about this, is that question 2 that says, is this UA value realistic? Wants you just to consider these aspects, to consider. And you can spend days on it, I know. So, but just as a preemptive measure to make you aware of, it is not for all designs. It's not the values that Elizabeth gave in TUTS. It is dependent on how you design your reactor, and this thing is dependent on the material of construction, flow rates, what is the fluid, the viscosity, the what is it, linear velocity, and in that inside your tube, the viscosity of the type of fluid that you have on the outside in your shell side of your heat exchanger. That's typically what you will have to consider. Right, so questions on this? Heuristic in the bundle ratio. So, okay, I understand what you're asking. So you want to say, am I going to have that and that? There are no heuristics for that. So what you will choose first, so what he's asking is if I've got my tube diameter and my bundle diameter, there are no heuristics. Your bundle diameter, let me get a whiteboard. Text article, no, I'm sorry. I am sorry. There are some in chapter 4 in Vogler. No, man, you're going to have fun. In Vogler, he gives some references. I will give you those references when it gets to your design part. It's also on the document that I distribute, where he says these are handy papers where some other people summarized some heuristics. The heuristics are different for very exothermic reactions, for endothermic reactions. Okay, so, and it is always first and foremost that you need to keep safety in mind. Safety must also form part of the way that you plan your heuristics, use your heuristics. Let me just share a whiteboard. Yuri's question. So, tube to tube bundle. How do they relate? There are no heuristics, but they are very good text, and it should be in your textbooks. Chapter 6, yes, that one. Product and process design principles. Thank you very much. That is what I am after. And that is in Coulson and Richardson. No, Coulson and Richardson. Volume 6. Volume 6. That is one of the most useful books for chemical engineers ever. Right. Okay. So in this tube bundle thing, what is important is the number of tubes that you choose must fit in there. So there are no heuristics. It is a calculation. So the tube bundle is an equation that is based on the number of tubes, the tube diameter, and your pitch. And pitch meaning, how do I want to arrange them? Do I want them like this? Or do I want them in square arrangement? Or do I want them in triangular arrangement? So how do I arrange the tubes? And then there are lots of equations. So that's just plug it in and just get the answer for your bundle diameter on how to fit them in. So those are well-developed equations. Are any of you familiar with this? Calculating a reactor bundle diameter if you know the number of, or a heat exchanger, because that's basically what you are designing, is a heat exchanger. Can you recall that maybe? calculating a bundle diameter? Anyone?
That part we
Yes or no?
did not do.
Vaguely remember. Oh, well, vaguely is better than nothing. This is the kind of stuff that vaguely remembers is all that is expected, because it's not something that you need to understand. It's equations that you go and say, oh, yes, we did it then, and now you can apply it. Okay, so it's not of any concern if it's just a vaguely, yes, somewhere there's a misty region where we might have plotted through it on our journey of survival through this course. That's fine. Okay, you will be able to find it this there and Google engineering toolbox, engineering toolbox. That previous slide that I showed you, just go and look in the recording. It's got very useful information with references on where to and on heuristics. That's a very handy site on that previous slide, engineeringtoolbox.com. Okay, right. Any more questions? Okay, this is a long one. When would we start to take porosity of the catalyst? This is such a good question. Watch this space, watch this space. This is definitely going to affect an area, okay? But it does not affect the heat transfer area. So let me just get a clean slate over here. So Josh is preparing you for our lectures of next term. My catalyst itself, this little zoomed in on my catalyst particle, is not a solid ball that looks like a goon, like a steel goon. It's got lots of internal surface area. It looks like a sponge more, but a solid sponge, right? And he's asking, so we've got two porosities that we are going to consider. We've now placed these little catalyst spheres in our reactor, and then due to that arrangement, we've got a bed porosity. What's the open area in the bed? But in my catalyst, I've got a catalyst porosity. And often in the design, I see people confusing the two, and that comes with heavy penalties. Don't confuse the two porosities. The area in here does not affect, because we assume steady state. We assume that the heat transfer is sufficient. I choose my heuristic so that my tube diameter is small enough so that I neglect any radial temperature differences. That is what I must ensure. And then if I don't have any radial temperature differences, I don't have any temperature profile differences over the diameter of my catalyst particles. So the area for heat transfer is only to do with that piece of steel that is there with or without the catalyst present in my reactor. The catalyst affects the flow path and the velocities that may affect the HI values, the heat transfer coefficient values, and that's only the bed porosity and not the porosity of your catalyst particles. And so you are absolutely right. It makes small little tubes for the reactants to flow through. What we are going to assume is a homogeneous temperature profile. So what that means is if I model the temperature over the volume of my reactor, let me just not on my OneNote anymore. If I should model the temperature over the volume of my reactor, and that is now that whole thing with the tubes there, as I now flow through the reactor, and it looks like that. We assume that in my tubes and also in the catalyst particles, as they are at different positions in the tubes, there are no profile over the catalyst tubes themselves. So I don't have a temperature over the particle profile, if you understand what I'm saying. So there are no hot spots on the inside of my catalyst and out. Okay, of course that may actually be true, but we are definitely going to assume that does not take place in our reactors in this course. Also, we are not going to consider a temperature profile if I now consider my tube, the tube that says I've got hot spots in the middle of my tube itself. So for my tubes, I've got a temperature over the diameter of my tube, and for each position, it follows that temperature that you calculate using your energy balance. So it's not a stupid question at all. Right. Any more very good questions? Of course, it's interesting. That's why you chose to study this. It is interesting. It is just overwhelming at this stage, but it will, hopefully you can get some joy in some of the stuff that you are learning. So yeah, I'm glad you realized that it is interesting and not just one more thing that you need to remember or add to your pile of things to um, clutter your brains. Okay, more questions. Somebody typing, put up a hand if you are busy typing before I stop the recording. Okay, so stopping the recording.